And finally, our last video in the sequence, we're going to talk last about lenses. And the nice thing about this is that most of it is a review of mirrors. So we have a lot of the same vocabulary, the exact same mathematical relationships. The only difference, well, a couple of differences, but the key difference is that with a mirror, when light hits a mirror, we expect the light to bounce off the mirror. So things that are happening behind the mirror are virtual, and we saw that we had to negatize anything happening behind the mirror. So if we formed an image behind the mirror, we had to say the image distance was negative. The height of the image was negative. If we used the focal point behind the mirror, then we had to make that negative. It's kind of the same idea here, but obviously with glass lenses, light is going to pass through the lens. It's going to refract. That's why you had to study refraction first. But I expect the light to do all its activities on the other side of the lens. So it turns out with lenses, if things happen on the other side of the lens, we treat that positive because that's what it's supposed to do. And therefore, if something happens on the same side as of the lens, then we'd have to treat it negative. So for example, here's a convex lens, actually double convex, and light passes through the lens. It technically refracts at each boundary. We'll talk about that in a second. It forms a focus over here. Well, I expect the light to do that. So this focal length will be treated positive. If I look at this double concave lens, also known as a diverging lens, the light passes through, it refracts here, it refracts again here at each boundary, and now it goes away, so it's diverging. But it acts as if the light came from this focus. And so the focal point is on the same side, so we'd actually make this focal length negative. And again, this is the way I do it in my class. Some books do it the same way, some books do it a different way. I'm going to teach you the way that I've always done it. But if you read in a book, you may see slightly different rules for signs. Just pick a method and follow it. You should be fine. So just like we have concave and convex with mirrors, we have concave and convex with lenses. Technically, because they have two surfaces, we have to look at both surfaces, but we're only going to do convex, convex, or double convex. So I'm just going to call it convex from now on. And concave, concave, both concave on both sides. I'm going to call it concave from here on in. Now, a convex lens, it has the exact same background as our earlier discussion. We saw with mirrors we had one surface. Well, because lenses have two surfaces, we have a surface on this side and we have a surface on this side. Therefore, again, they're all spherical. So this side of the lens is part of a bigger circle, and so we have a center over here, which we actually call C prime or 2F prime. And then we have a focus halfway to the vertex, which we call F prime. We only use primes to distinguish the same side from the other side. We have the other side of the lens, and again, same idea. We're going to have over here an F and a 2F, sometimes called C. So different books call it different things, but it's the same basic geometry we had before. We still have our principal axis cutting through the center, and the vertex, the same vocabulary. The only other point of note is because the lens itself has an optical center, we often pick this point, and my smartboard's not calibrated too well, but this point right here is called the center, so we don't confuse it with the other center. We usually call this O for origin. So you'll see that's important for our rules for doing ray diagrams. Now, and the same thing, if we have that was a double convex, we can also have a double concave. And again, I do the exact same thing. I have an origin, I have an F and a 2F out here. These are the primes. We have an F and a 2F over here, or sometimes we call it C. Same idea on that side. I usually make the left the primes and the right is the regulars, and this is where I put the object on the left-hand side. Now, again, I want to make sure people really see what's really happening, but we kind of cheat a little bit. So I'll draw, again, a double convex lens. We're going to have a light ray coming in. It's going to hit the lens. Now, it's a real hassle. We technically would have to calculate the refraction at that boundary from air to glass. The glass, it turns out, because it's more dense, it will bend towards the normal. It's going to hit this boundary, do the calculation again, it's going to bend away. It's a pain in the neck to draw. So what we normally do is this. We simply, knowing it's incorrect, but it's okay, we go to the center, and then we show the refraction. So you'll see that the diagrams are going to follow the rules. The rules are correct, but we're going to do an approximate path. Some books will actually show it correctly done on both boundaries, but when you're doing it in lab, don't bother. I'm going to skip over that. Now, here are the rules for ray diagrams. And again, they're the exact same rules as before, kind of. But when we did mirrors, we said a light ray from the object parallel to the principal axis will pass through the lens and go through the focus. So remember, in parallel down through F. Well, it's the exact same thing, except now the F is over here on this side and 2F is over here. So we send a light ray in parallel. So we'll go to the top of the object, come to the center, take it down through F. That's the first rule. That's rule 1. Rule 2 is actually, this is actually easier than before. It says a light ray through the center, the center point, is going to strike the lens and pass straight through. Now again, this is really because of refraction. It turns out when you do the calculations, this will actually occur. I didn't do that too well, but these two should meet down here somewhere, and we'll get an image formed. So here's A prime, and here's the image. Again, my smartboard's not calibrated too well, so it's not perfect. And we have a third rule. It says if I send it into F prime, and again, we don't often use the third rule, but if you need to in some cases, so I have an F prime on this side. If I send a light ray down through F prime, it's going to go through F prime, hit the lens, and then refract out. And again, it will pass through the same point. So all three rules work just like before. So copy down the rules, and we'll get a little practice doing a little lab. But the rules are the way which we figure out, oh, if I hold the lens here and hold an object here, the object will be bigger, inverted, real. We can describe all the various cases. So online you can download the lens ray diagram sheet, and you can go ahead and do those. Take a ruler. You do not need to use a protractor. Just take a ruler and use the rules I just showed you. The cases are identical. There are cases 1 through 7. 1 is done for you like it was done before. The tricky cases are 5, 6, and 7, where things act strangely. You want to describe the image on there. Then you can also download the answer key. So there's an answer key there that will show you it, but I really recommend you do it by hand first, then download the answer key and see how you did. Not only doing the ray diagrams, but describing the images. Look at the image compared to the object, and you'll see what happens. Now, the equations are also exactly the same. The equations for lenses and the equations for mirrors are identical. So we're going to have our 1 over F equals 1 over DI plus 1 over DO. That's handy for calculating F. And you can do it for calculating DI and DO. Usually when I calculate DI, I use FDO divided by DO minus F, and DO equals FDI. DI minus F. I do the exact same thing. We also have high over HO equals di over DO. And the magnification is the absolute value of that. We ignore our sign rules for that. Now, the only thing, as I mentioned a moment ago, the only difference with this are the sign rules. So with a mirror, I expect the light to bounce off the mirror. So things that happen behind the mirror are negative. For lenses, we expect the light to pass through the lens. Therefore, anything that happens in front of the lens will be determined to be negative. Now, this could be the focus. So the focal length could be negative sometimes. The DI certainly can be negative sometimes. And the HI. Remember, negative means it's on the wrong side. It doesn't mean it's inverted or something like that. Different books do it differently. I use the method I use. And again, you can choose to use my method or a different method. It doesn't matter, but just be consistent in how you apply the sign rules. And again, the same thing. You can do a calculation. So most of the time it's plug and chug. You plug in the values. You look at, say, focal length is 10, the object height. You place a certain place, think about the cases, do the calculations. There will be a homework set online. You can try these. In the solutions, the homework are done there. So you can try a couple of problems. Again, you might want to stop the video and try the calculations, see what you get for an answer. Then look at your key for the ray diagrams. Look at what case it is and see if it makes sense for what you did. Once you know how to do it, it's easy. And again, we'll talk about these in class, and we'll do a couple of cool little labs where you play around and actually form images with lenses. The lens lab is kind of a fun little lab to do. There's obviously, this gets into how glasses work. Most of you have contacts or glasses, and if you don't have them yet, you eventually probably will. Lenses are used obviously to get the image to form in a proper place. So if you're nearsighted, which some of you may be, the image is forming not on the retina, it's forming before the retina. You put a diverging or a concave lens in there and it actually forms the image on the retina, and then your brain sees it. If you're like me, I'm farsighted. I have great vision far away, but I can't see anything close. I have a cheap pair of glasses that allow me to, a converging lens which brings the image from behind my retina onto the retina so I can see clearly. So we all take advantage of this refraction process. And again, we'll do a little mini lab in class. And sometimes we go outside and set fires in the grass. It's kind of fun to do. Here's some pictures from last year. Here's a kid's apple. We projected a real image of an apple onto a screen. Here's somebody's hands projected onto the screen. This is a real image. Somebody's real optical representation of their hands are projected onto a screen, which is kind of cool. And then we'll do a review and do a test. So that's the last of our videos. Hope you survived.